All right, so the lesson for today is bond energy, and this is the third lesson in Unit 3. We're going to talk about bond energy in various compounds as well as bond length, and how we can use bond energy to calculate enthalpy. And we learned enthalpy yesterday. All right, so first, ethylene was something we learned last unit. Carbon, triple bond, carbon. The 2-carbon alkyne. It is a colorless hydrocarbon that we commonly call acetylene. And acetylene is a fuel. And we typically burn acetylene in blow torches because the flames can produce a temperature greater than acetylene will release a lot of energy. But how much energy? How do we calculate the amount of energy released from burning acetylene, or anything for that matter? So in order to do that, we need to use bond energy, all right? And there's something called bond dissociation energy. Dissociation means to break apart. So bond dissociation energy is the energy required to break a bond. And last time we learned that if you break a bond, you will need energy. You need energy to separate the two atoms from each other. So if you have methane, CH4, and if you add 413 kilojoules per hydrogen, you will break up the entire methane into just atoms. All right, and if you have carbon and 4 hydrogens separate, and they happen to combine to bond to make methane, you will produce around 413 kilojoules per bond. So energy will be released when you form bonds, and when you want to break a bond, you need to consume energy. So this was also from yesterday. We have here a table that basically tells you the bond energies of various types of bonds. You can have single bonds or multiple bonds, and notice that multiple bonds are found on the bottom of this table. Now, if you just go through the table, you're going to see a lot of different bonds. It starts with HH bond, so the bond between hydrogen. You can see that in the black column to the right. The energy for that bond is 432 kilojoules per mole. That's the unit. And the length of that bond is 74 picometers. All right. And if you go down the list, you see the halogens, HF, HCl, HBr, HI. They all have their own unique bond energies. And if you go down further, you have the carbon bonds, CH, CC, CSI. All of those bonds have their unique bond length. Now, there is a difference between double and single bond. Carbon, single bond carbon, according to this table, is 347 kilojoules per mole. But carbon double bond carbon is not simply double that, okay? If you go down to the bottom, you can see multiple bonds. Carbon double bond carbon is actually 614, not exactly double of a carbon single bond. And a carbon triple bond on the right side, you have 839. So if you want to talk about the bond energy of double or triple bonds, you can't look at it as 2 single bonds. It doesn't work that way. It has its own unique bond energy. So basically, all of the potential bonds that you will see are found in here. Okay, of course, there are more bonds than this, but these are the most common ones. So you can just refer to this table, the list of bond energies, and use these values to solve problems. All right, so let's look at methane in particular. You have to know that the values in the table are averages. What does that mean? Well, imagine methane, CH4. We have 4 hydrogens for 1 carbon. If you remove the first hydrogen, well, you need energy for that. How much energy? Well, the first row says 435 kilojoules per mole. All right, if you want to remove 1 hydrogen from methane, you will require 435 kilojoules per mole of methane. If you want to remove a second hydrogen after having removed the first one, so you have CH3, and you want to take away a hydrogen to make CH2, well, you are going to need 453 kilojoules per mole. So it's a little bit different. And then if you want to remove a third hydrogen, that is again different, 425. And then if you want to remove the last hydrogen to make just carbon, you have 339 kilojoules per mole. Okay, all of these are different. And they average out to be 413 kilojoules per mole. So we use the average of the CH bonds and not the individual bonds for simplicity. All right, so the amount of energy that you need to break a bond, it depends on how many bonds that carbon or any atom already has. So that table is a table of averages, and we're going to be using the table of averages. So again, for multiple bonds, this table compares the difference between single, double, and triple bonds. For carbon-carbon bonds, the bond length, you can see that it decreases as you have more bonds. All right, so carbon-carbon single bond has a bond length of 154. And that length will decrease to 134 if it's a double bond and 120 if it's a triple bond. All right, and the bond energy will increase if you increase the number of bonds. Okay, so this pattern holds true not just for carbon-carbon, for any other atoms. The carbon-oxygen, single-double, well, if you compare the bond length, the double bond has a shorter length, but higher energy. And carbon-nitrogen, same story. Carbon-triple bond nitrogen has the lowest energy, but the lowest bond length, but highest energy. All right, so just know that as you increase the number of bonds with the same atom, bond length will shorten, but bond energy will increase. All right, so how do we calculate enthalpy using bond energy? All right, it's actually very simple. The enthalpy change, well, that's the only thing we're concerned with, the change in enthalpy delta H, that is simply the sum of energy required to break all the bonds plus the sum of the energy release in forming the new bonds. All right, so how much energy you need to break up all of the bonds plus the amount of energy you will release after you assemble it again. Okay, so that is delta H. And keep in mind that if you break a bond, you will need energy. So that will be an increase in energy, so positive number. Whereas if you release energy when you make new bonds, and the release of energy should be a negative number. So that's why I have bracket positive and bracket negative. So to put this mathematically, delta H is equal to sigma n times D minus sigma n times D. Okay, now sigma means sum. Okay, in mathematics, I don't know if you've seen this before, but sigma is the notation that we use to represent a series of sum. N is the amount in moles, and D is the bond energy per mole. And all of these values you should be able to determine or look up. And then you can just plug it into this equation, and you should solve for delta H. The first sigma adds up all of the energy needed to break all of the bonds. So that's energy required. Subtract all of the energy released. So that is the sum of all of the energy released. You subtract that energy because you release it. You don't gain that energy. And the difference could be positive or negative. That will tell you delta H. Okay, so do we have any questions so far regarding what this equation means? All right, so let's use this equation. So here is example 1. Using the bond energies table, calculate the enthalpy change for the reaction in which hydrogen gas is combined with fluorine gas to produce 2 moles of hydrogen fluoride gas. So H2 plus F2, you get 2HF. Okay, that is our reaction right here. We need to calculate the enthalpy change, delta H, for this reaction. How would you do that? Well, you have to determine the bond energies for all of the bonds that exist in this reaction. In the reactant side, you have H2 and F2. The bond that holds H2 together is an HH bond. Okay, two hydrogens bonded together. You could just look at the table and figure out that the bond energy for HH is 432 kilojoules per mole. How many of this do I have? I have one HH bond, right? I have one molecule of hydrogen, H2. That means there must be one bond that is HH, so that is N equals to 1 mole. And you do the exact same thing for fluorine. The FF bond, how many bonds do you have? You have one, because you have one fluorine molecule. And what is the energy of that bond? If you look on the table, that will be 154 kilojoules per mole. And you just copy that down, and then you work on the right side. So those are the reactants. What about the product? The product has just one compound, HF. So you need to look at HF on the table. How many HFs do I have? Well, according to the balanced equation, I have 2 moles of HF for 1 mole of hydrogen and 1 mole of fluorine. So the answer is 2. Each HF has one HF bond, but there's 2 of them, so 2 moles. The bond energy is 565 kilojoules per mole, as indicated by the table. Okay, does that make sense so far? So you understand how I get these values. You just basically whip out the table and you take a look. And as for N, you just count how many bonds exist based on your balanced chemical equation. So now you have all of these numbers. You can calculate enthalpy using this equation. All right, so the sum of all the bonds broken minus the sum of all the bonds formed. So, all the bonds broken first. ND plus ND. Now, why is there 2 of them? The sum means you have to add up all of the reactants. Hydrogen gas, H2, is one of the reactants. So, how many moles of hydrogen times the energy per hydrogen? And plus, the second reactant, the fluorine, how many moles of fluorine times the energy per fluorine? All right, so in the brackets, you would have ND plus ND. Subtract the product. Okay, the product would be HF. So NHF, DHF. That's the only product you have. So that's the only thing you subtract. You do not need a sum for that one because you don't have a second thing to add to. Okay, so please make sure you have brackets. In this case, the brackets doesn't matter because it comes first anyway. But if you want to subtract the sum of all the product, you do need a bracket. In this case, I don't have a bracket because I'm not adding anything, so just minus. Now you substitute the numbers in. The moles of HH bond, well, there's 1 mole. As we mentioned earlier, I put in 1 mole. The energy per mole is 432 kilojoules per mole, as determined earlier. And you fill the same thing out for fluorine. 1 mole of fluorine, 154 kilojoules per mole per bond. So that is a reactant minus 2 moles of HF. So that's why the NHF is a 2 mole, and the bond energy per mole is 565 kilojoules per mole. So now the moles should cancel. Right? If you multiply and divide by the same unit, they're gone, and same thing here. You would have kilojoule minus kilojoule, which gives you kilojoules, which makes sense because enthalpy is measured in kilojoules. So you whip out your calculator, you could just punch all of this in, and you could just click equals, and you would get negative 544 kilojoules. Does that make sense? You round to the correct number of sig figs. In this case, everybody has 3 sig figs, so that's a no-brainer. Of course, it's 3 sig figs. So that's the enthalpy change of this reaction is negative 544 kilojoules. It can be a negative number. It simply means you release this energy. It is an exothermic reaction. Is this clear? Do we have any questions?
I have one question for the mole and like the bonds formed, like the energy of it. So right. Even if we have like 10 moles of molecules, the energy still doesn't change, right? Like it's the same thing.
The energy is per mole. If you have 10 moles, well, per individual mole, it should be the same.
Oh, okay. Okay.
Yeah, so the table number doesn't change. Your moles can change, but that value wouldn't.
Okay, thank you.
You're welcome. Any other questions? All right, so here's example 2. Example 2 is a longer problem. You have more substances. So using the bond energies table, calculate the enthalpy change for the reaction in which methane, CH4, is combined with fluorine gas and chlorine gas. That's a very deadly reaction. To produce Freon 12, which is CF2Cl2, and as well as HF and HCl. All right, so here is the balanced chemical equation. Calculate enthalpy change. Right? You're supposed to use the table, and you're supposed to count the different bonds. All right, so I'll give you around 5 to 10 minutes. Go ahead and try this on your own, and then I'll take this up. So this is quite a tedious question. It takes a long time to figure out all of the bonds, which is why I said this is going to be an annoying class, but it's not a hard calculation, so good luck. All right, so to find the enthalpy, you're going to need all of the different bond energies found in this entire reaction. Okay, and that can be very, very annoying. So determine all the bond energies of all bonds. So here's your equation right here. Let's start from the left side. Methane, CH4, well, it has 4 carbon-hydrogen bonds. So the moles is 4, not 1. You have 1 mole of methane, but for 1 mole of methane, you have 4 CH bonds. Okay, so N is 4. Bond energy for the CH is 413 kilojoules per mole. Moving to the right, you have chlorine, the Cl-Cl bond, and you have 2 of those because you have 2 moles of Cl. So that's why N is 2. And the bond energy, just look on the table, 239 kilojoules per mole. And for fluorine, same story. You have 2 moles of fluorine. So there are 2 FF bonds, so 2 moles, and it's 154 kilojoules per mole. Those are the reactants. For the products, you have CF2Cl2. In 1 molecule of CF2Cl2, you have 2 CF bonds and 2 CCl bonds. So that's why I wrote 2 different rows. The first row is for the CF bond. There's 2 mole of those, 455 kilojoules per mole. But for the CCl bonds, you still have 2 moles. This one is 339 kilojoules per mole. All right, so that's why I have 2 rows for that because there are 2 different bonds. HF, there's 2 moles of HF, and that means there are 2 HF bonds, so 2 moles, and that is 565 kilojoules. And finally, HCl, again, 2 moles of HCl for 2 moles of H and Cl bond. And the H and Cl bond, that's a typo, will be 472 kilojoules per mole. That takes quite a while to just list out. You got to flip back and forth, back and forth. You got to look on the table. Yes, this is very annoying. But once you get here, you can put all of these numbers into your equation. So in the reactant side, you have ND of the CH bond plus ND of the chlorine-chlorine plus ND of the FF in brackets. Okay, you have to add them all up. Subtract, again, in the big brackets, all of the products. So CF is a product. CCl, that's also in the product. HF and HCl, you have to add all of them up first. And then you subtract the 2 products, one from the other. Okay, make sure you have the bracket around both. Okay, the first one is just for organizational purposes. It doesn't change the answer mathematically. But the second bracket after the subtraction sign, that really matters. If you don't have the brackets, then all of those signs should be minus. Okay, please make sure you don't screw up. If you drop the brackets, you will get this wrong because of bed mass. And you're in grade 12. If you get a question wrong because of bed mass, you get laughed out of the building. All right, so make sure that you don't screw up the brackets. Then you substitute the numbers in. N for the H bond is 4, and then the energy per mole is 413. Basically, you do the whole thing. You just take all the numbers, pull it in. Make sure you put it in the right place. You know that which one is which, and you should get to here. Then you whip out your calculator. You should all have a relatively powerful calculator. You should be able to enter this entire thing into your calculator and press equal sign in one step. I don't bother calculating each one of these individually and do many calculations. That's very tedious and annoying. Just put it all in one step. Boom. You should have negative 1,194 kilojoules. All right, and so because it's negative, you know that this means that energy is being released. This is an exothermic reaction. Okay, so sig figs. Why do I have 4 sig figs in the final answer where everything I used in the reaction have 3 sig figs? Okay, so did I make a mistake? And why did I ignore the 4, the 2? Okay, they have 1 sig fig. I multiplied by 4 moles. I multiplied by 2 moles. How come they didn't count? Well, so just a little rant on sig figs. If you are counting something, you do not consider sig figs. You do not include the counting numbers in your sig fig calculations because you only have significant figures if you are doing a measurement that has uncertainties. If you count, you do not have any uncertainties. Okay, you're not going to count wrong. If there are 4 moles, you go 1, 2, 3, 4, and that's it. You don't have to tell me anything other than that because you got the number from the balanced equation and the number of bonds. So that does not count for sig fig. You can just ignore the 1 sig fig numbers. So that brings us to why is it 4 sig figs in the final answer, but 3 for everything else? The key has to do with this is addition. You add up all of those numbers. You don't multiply them. In multiplication and division, you round to the least amount of sig figs you used. But in addition and subtraction, you round to the least number of decimal places you used. And none of those things have any decimal places, so your answer should not have a decimal place. That's the only rule. If you add up to like 4 digits, that's fine. Just don't have any decimal place. So in this case, that is the correct number of sig figs. 4 digits, no decimals, okay? So I hope I made myself clear regarding sig figs and regarding this question. So anyone have a question to ask? No, we're good? All right. All right, so here's example 3. Again, using the bond energies table, determine whether the complete combustion of ethylene, C2H2, to carbon dioxide and liquid water is exothermic or endothermic. I'm going to stop you right here. You can basically tell me the answer right now without doing anything because you have common sense. What is it?
Exothermic.
Exactly, exothermic. How do you know that?
Because it's a combustion reaction, and in combustion, energy goes out. Yeah.
Exactly. Thank you. That feels right, doesn't it? Like that's right there. That's the answer, right? The whole point of burning ethylene is to generate heat, and you can use that for something. That's the whole purpose of burning anything, to generate the energy, and then we can use that energy. So of course it's going to be exothermic. So let's just prove that it is exothermic mathematically. All right. So to do that, you have to balance the equation, and you have to draw the Lewis diagrams. I'll do this part for you because that is something we learned quite a while back. Let's not waste time on that. Write a balanced equation. You have a complete combustion of ethylene. C2H2. Complete combustion means you burn with oxygen and the products are carbon dioxide and water. Okay, so you balance the equation like that. Now, why is there a 5/2? Why don't I double everything? Well, in grade 12, we're allowed to have fractions for the coefficients, okay? Because sometimes it is more convenient to view one of the products as just 1 mole. In this case, it's C2H2. You could multiply everything by 2, and it wouldn't make a difference for this question. But I suggest you get into the habit of using 1 mole to represent a certain substance, because later down the line we're going to be learning calculations where you have to have just exactly 1 mole for a particular thing, and you're allowed to divide whatever number you want so that it has 1 mole. All right, so we can use the 5/2. That is not a problem. So once you have the balanced equation, the product being carbon dioxide and hydrogen, and water, you balance this. All right, cool. Moving on to the Lewis diagram. Why will we need to draw the Lewis diagrams? Well, if you don't draw the Lewis diagram, how would you know what kind of bonds are present, right? Because we're talking about bond energy, and to know that, you got to know what bonds are present in your molecules. Two carbons, why any triple bond? So that's it. Carbon dioxide, CO2, double bond, a linear structure, oxygen, O, double bond O, and then water, it's a bent H2O molecule. So now you can clearly see which atoms have what bonds. Okay, knowing this, you can start to look at the table and figure out all the bond length. Sorry, the bond energy. You don't really need the bond length. So I'll give you some time to work on this question, around 5 minutes, and then I'll take up the answers with you guys again. All right, so once you write the balanced equation, you draw the Lewis diagram, it's time to bust out the table and figure this out. So for the first one, ethine, C2H2. Inside of an ethine molecule, you have 2 CH bonds. Okay, each carbon has 1 hydrogen attached to it, so that's 2 moles. And a CH bond is 413 kilojoules per mole. And ethine will have 1 triple bond between the carbons. And so 1 mole, and therefore a triple bond between the carbon is 839 kilojoules per mole. And you do that. So the same thing for oxygen. There are 5/2 oxygen, so 2.5 moles of oxygen. But there's only 1 double bond between each, so that's 2.5 moles. The energy per bond is 495. But CO2, see, here's where it gets tricky. You have 2 moles of CO2 according to the balanced equation. But each CO2 has 2 double bond oxygens. So it's 2 times 2, 4 moles of C double bond O. Okay? 2 CO2 molecules, each molecule has 2 bonds, so 4. And each of those bonds has 799 kilojoules per mole of energy. Water, well, there's only HO bonds, and there are 2 HO bonds per water. That is 467 kilojoules per mole. So once you looked on the table and once you worked out how many moles each bond have, then you can substitute into this ugly long equation. Just make sure that you write it out properly. All right, so the reactants, well, the CH bond, C triple bond carbon bond, and O double bond oxygen bonds, all add them up. Subtract the products, which has C double bond O, the carbon dioxide, and OH, water. You plug in your numbers carefully. And yeah, this will take a while. But if you just one by one, make sure you don't plug in the wrong number to the wrong place. You carefully plug this in. You whip out your calculator. I know this is long, but I believe your calculator should be able to do this in one step. Don't bother calculating the first part, write down the number, and the second part, write down the number. That's a waste of time. I highly recommend you do this in one step. If your calculator for some reason is unable to do this in one step, then I suggest you burn that calculator and get a new one. All right. So put it in, boom, negative joules. And since this number is negative, this means it is exothermic, which confirms our prediction. Okay, so that makes sense, guys? All right, so that's it. We learned bond energy today and how to use bond energy to calculate enthalpy. Okay, if you break a bond, well, that's endothermic. You need energy for that. If you make a bond, that is exothermic. You release energy. And more bonds you have per atom, the higher the energy. Okay, and the more bonds you have between two atoms, the shorter the bonds. And that's it. Any questions? All right.
So you would tell us which chart to get our bond energy from, right?
Yes. Yep.